Give you that time, check your answer, move on to D, and this will be it for Revolution at this point. For at least for now. We'll probably practice some more next week, but for now, that'll be it. So working on 4C with these, and I really honestly would encourage you to think about it like this. Step one, you got to ask yourself, based on your ability to visualize this, will there be a gap or a hole in the solid? And your answer should be yes. And if your answer is yes, then I would suggest that you go immediately to a washer method framework. So that would be V equals pi integral, we'll do the limits in a little bit, of big parentheses squared minus little parentheses squared. And then our next step is to figure out the dy or dx. So step one, will there be a gap or a hole of any kind? If the answer is yes, go washers. If the answer is no, you just go with discs, right? Okay, so we're going with washers. Now I got to decide, is it going to be a dy or is it going to be a dx? What do you guys think?
dy.
dy. Anytime you're rotating around a vertical whatever, whether it's the y-axis or some other vertical line, it's going to be dy. So I'm going to go with dy right here. And then in our efforts to continue to fill things in, I'm going to draw in a little representative rectangle, which will become a representative washer. Do these horizontal, the dy rectangles, do they accumulate from left to right or bottom to top? Bottom to top, right? So next thing I'm going to do is fill in my limits of integration, because that's going to tell me where I start and stop accumulating. So in this case, from bottom to top would be from where to where? Yep, y equals 0 to y equals 2. So I'm going to fill that in right here. I was talking with Delaney back there. If you get kind of stuck on these, at the very worst, Laney, sorry. If you get stuck on these, at the very worst, if you can get that up there, very often from a credit perspective, you would get a point for that, simply because you knew that you had to do an integral, you knew there was a pi involved, you knew that it was 0 to 2 and it was like a difference of something, and maybe you like messed up the rest of it, but in most cases you'd at least get a point, right? Because you do know something about this, right? Often like the integral, the limits, and the pi would be a point. So anyway, to finish this out though, we want to try to get, of course, the radii correct. And so we're going to go with big radius squared minus little radius squared. I want to get rid of that for the moment. So we go 0 to 2. And let's look at the two radii. So I am going to try to represent the radius, the big radius in orange. So wouldn't you say that the radius, the big one, goes from there to there? From the axis of rotation all the way over to the red line. That's the outer surface of this solid. Okay, so then, anybody have any suggestions on how to quantify this? Clearly, depending where you are, it's different, but what could you say? Any ideas? Okay, let's talk about it. So we could start with that. Colin, your idea is quite good. It really is. So last time we talked about kind of a general idea here. You can go axis of rotation minus the appropriate function. This will always work. So you can go axis of rotation, which is -3, minus the appropriate function. And so Colin just suggested, an x right there. And he's right, because from here out to there, that really is just an x. So I've got no problem with that. But we know that in the end, we're going to have to replace that x with something in terms of y. So if it's that line, what is the line equal to as far as x equals whatever? Is it 2y? I don't have I think that's right. I don't have it in front of me here. So minus 2y. Okay, and then of course the small radius in blue here goes from here to there. And so this is going to be very similar. This is going to be -3 minus the appropriate function. And I forget what it is. Is it? Oh, it is. It's root x. Okay, so y squared, like so. So it's at this point you might be a little leery of this, because if you just look at only this part right here and only this part right here, those will end up being negative numbers, won't they? Why is that not a big deal? We're about to square them, right? So the ordering of the difference in this case really doesn't matter because of the squaring. And so that's for that reason, I always go axis of rotation minus appropriate function when it comes to finding the big radius and little radius. Okay? If you want to monkey around with it and be like, oh, actually it should be the other way around, that's fine. no problem at all. But I just think this is faster. Any questions? Let's go okay? Question?
Just a little bit. So I put the calculator and they're the same, but if like you thought about it, like you're rotating around. It's like the graphs have been shifted to the right 3.
Yep.
And you're just rotating around the
Yep.
x-axis. So you could just like change the equations to just like
Yep.
2y plus 3.
Yep.
That'd be fine. Or it's just different in B because the negatives were swapped for the functions
Mhm.
in 5.
I totally agree. Like you could like unshift everything or shift different things, I guess. And I've seen people do that at the reading, and it's very possible to navigate all that. I think in most cases it ends up getting more complicated because, like you said, okay, in B the negatives kind of got messed around with a little bit, and you have to maybe rethink it through a little. But I mean, it can work. Just be really careful. I think this is the best way, only because to me it's simple. I like simple, but if your brain doesn't work that way and you'd rather do some other shiftings, that's fine too. Yeah. Anyone else? Okay, well, let's tackle this last one here, 4D. Write but do not evaluate an expression for the volume of the solid if that same region is rotated around the horizontal line y equals -2. Ready, set, go. Start off like this. Why don't I just show you what this would be, and I'll let you guys discuss questions as needed, okay? So I would say volume, it's definitely going to be a washer method. Volume equals pi. Integral, did you guys have 0 to 4 for this one? Because we're doing x's, we're going from left to right instead of bottom to top. And then it's going to be big parentheses squared minus little parentheses squared. And it's going to be a dx this time because we're rotating around a horizontal instead of a vertical. And so then as far as the radii go, it's going to be axis of rotation minus something in both, right? And so for the first one, the further away function is the curve, that's root x. And the closer function to the axis of rotation is the line x over 2. So that would be one of the ways you could write this to get the volume. So I know I did that quicker than the other ones, but I have the sense that we're starting to really pick this up. I feel like I'm onto something there. Are you guys doing okay? Does that make sense? Any questions? Big ones, little ones? Anything? Okay, we good? Okay, well, let's do this. Let's finish up real quick. We just got a few minutes left here. Let's finish up with cross sections. So if you would, this is that thing that I showed you that's a little bit different. And this is it. We got 4 examples left. We're done with the notes. And after that, we'll just practice. So we probably finish this on Monday-ish. That'll give us a couple days to really get in some, hopefully, really good practice in preparation for the last, the quest. So anyway, these solids are not caused by rotation, like as I compared and contrasted earlier, but I'm calling it a sliding of a cross-section or an accumulation of a cross-section over a particular region. I want to give you the formulas here. The formulas are pretty simplistic, but I'll have some explaining to do for sure. So this is different than rotation, so it's going to look like this. Volume equals the integral from a to b of a of x dx, or volume equals integral from c to d of a of y dy. So essentially the exact same formula, right? I just put c and d because they could be different numbers. They don't have to be the same as a and d. And so these formulas basically just have one thing. It's the a of x or the a of y. And what it is it's highly adaptable. A of x or a of y stand for the area of a cross-section. The area of a cross-section. So if I could, I think I've got time to do this. I thought I would sketch something out here real quick. I think I've got room to do it. Are you guys okay with this being the y-axis in perspective and the x-axis again in perspective? Does that make sense? It's like, you guys know when you draw like the train tracks, you know how the train tracks meet out there somewhere in perspective?
so it's like we're looking.
It's like we're looking at it kind of from up and behind instead of like straight down on top. It's not like the y-axis went.
Yeah, that works. Yeah, it was like straight on top.
It's not like that. It's intended to be like a 3D drawing. If I wanted to draw it like that thing you saw earlier, I could put in a z-axis going straight up and down. Does that help? So it'd be like a Z.
I hate Z.
Anyways, so let's say we created something like that other graph. And this is decidedly lower tech than that graph, but maybe this will be helpful. Let's say you've got some region hanging out there. We've done regions like that. We've rotated those, and we found areas of those. This time, that region's just going to sit there. It's not going to go anywhere, but things are going to grow up out of it. So I'm going to try to represent that for you with some green. Let's say we did squares again, kind of like earlier. Let's say the squares are perpendicular to the x-axis. Is the perspective starting to make more sense? So then, the way this works is you can see that depending on where you are on the region, the size of the square is going to be larger or smaller, right? Depending on where you are. And so this function, a of x or a of y, is going to be able to adapt to the shape of the cross-section. So for example, if the cross-section was squares, right? What's the area formula for a square? Say again? Side times side, base times side. How about side squared? Yeah. Same thing? Yeah. So if it was a square cross-section like this one, then you'd use side squared. Like a of x would be side squared. However, you could have others. You could have other cross-sections. If your cross-sections were triangles, what would a of x or a of y be? 1/2 BH, right? And so these can be highly adaptable to whatever shape the cross-section is. Let's say it was a semicircle. What do you think the area, what do you think a of x or a of y would be there? Yeah, pi r squared over 2. And believe it or not, you could have like cross-sections that are pentagons, rectangles. We'll probably stay away from regular polygons like pentagons and all that sort of thing. Could be really any shape. Okay? So when you come to class on Monday, we'll probably do some more demos and some more Play-Doh, and we'll get into our examples with these. So hope you have a good weekend. And if any of you want to talk about this stuff I talked about at the start, love to talk to you. I mean, I don't know if I have anything really to add, but always happy to hear or talk. So see ya.